Our speaker today is Pamela Freeman. Pamela is a postdoctoral fellow here working with IRA Palau. She joined our institute last year, yes?
Yes,
in September, after finishing her PhD, which she obtained from University of Calgary in Canada. And during her graduate work, Pamela designed developed a correlator for the Dominion Radio Astrophysical Observatory. I had looked that up what a correlator was since I'm not a radio astronomer. So if you don't know, some of you, correlator is the one that combines signals from multiple radio antennas and gives you all these beautiful high resolution images. Okay, and while doing that, she also studied how complex molecules form during the star formation process. And she also finished a science communication internship at the European Southern Observatory. So today, Pamela will share some insights on astrochemistry with us, and she will also tell us how the NGVLA will transform this. Thank you.
Thank you for the introduction. It's my pleasure to be here today talking to you all, and unfortunately, on the day that there's no coffee, hopefully you'll stay awake enough to pay attention. If not, I understand. First off, before I get into astrochemistry, I'd just like to acknowledge that this work, if the clicker works.
Okay. The whole thing is not.
There we go. Okay. I would just like to acknowledge that this work is done in collaboration with many other people. So throughout my graduate studies, I had the supervision and mentorship of Joanne Brown and Renee Plume, the two on your left there. During my PhD, we worked closely with collaborators in France, Sandrine Bottinelli and Manuel Co. You might have seen Emmanuel around here in this past year. We collaborated with Baswadi Mukherjee out in India. Renee had an undergrad student, Chris Monahan, who was really pivotal for my first paper. And then now I'm working with IRA Palau here at IRYA. So this picture, the Dominion Radio Astrophysical Observatory, a really big radio observatory in Canada, is just shown here. I just like to show it off because it really is a special place and really helped me develop my skills in radio astronomy. These dishes represent the synthesis telescope that I did develop that correlator for. But over into astrochemistry, what I'm doing here at IRYA, we're going to start a very big picture. So we have in the interstellar medium clouds of gas and dust. These will collapse under gravity to form new stars. This process of star formation also creates an evolving catalog of molecules. By studying this molecular emission, it gives us both a view of the current physical conditions that are in those regions, and we can actually analyze that data a little bit to look at the evolutionary history of those regions. So if we start with our molecular clouds, just that in the diagram in the top left, these will collapse to form what we call protostars. So not quite when the star has turned on hydrogen fusion, but when the star is undergoing formation. These protostars will have a accretion disk around them, which will eventually become planetary systems. And so if we take a kind of more tangible look at that protostellar evolution, we start off with the prestellar core, again in the top left of this diagram, that is contracting under gravity. When we have the onset of a protostar, we call it class 0. That is when it's still really enshrouded in its parent envelope. But you do have the start of seeing some millimeter emission in those sources. Moving on to class 1, you start seeing a little bit more structure. There might be a disk already starting to form, have some outflows, but it's still quite enclosed in that parent envelope as well. Moving on to class 2 protostars, those will start to have really dissipated the cloud around them, starting to form much more structure in the disk and really seeing that outflow clearly. And again, over these stages, it's getting more and more compact. Moving on to class 3, the cloud is completely dissipated around it. You still have that accretion disk around the compact object before becoming, at the bottom left here, a full planetary system. You have your star and your planets orbiting around it. For my research, we're going to focus on the class 0 and class 1 stages, where you do have structures starting to form, the disk, the outflow, the compact object, but still quite enshrouded in its parent cloud. But I do want to start with the chemistry a little bit at the pre-stellar cloud stage. The chemistry that can happen here could be inherited in later evolutionary stages, and so it's really important to look here. So in these dark pre-stellar clouds, we could have molecular depletion from the gas phase onto grain surfaces. On those grain surfaces, you can have chemical reactions forming larger and larger molecules. You also, even though the gas is cold, and by cold I mean about 10 Kelvin, maybe up to 20 Kelvin, you can have some cold gas phase chemistry. And so we do start to see the beginnings of some complex molecules in these sources. But if we move on to the next stage, those protostellar sources, we have different regions that could have different chemical reactions happening in them. In the protostellar core and in the envelope, in the gas surrounding it, we can have warm or hot gas phase chemistry. By warm, I mean about 20 to 100 Kelvin, and by hot, I mean 100 Kelvin or more. You also have non-thermal or thermal mechanisms breaking off molecules from those grain mantles back into the gas phase. And so that can be another important source for the molecules that we'll end up seeing in these sources. And I do just like to note, this is a very incomplete overview of the chemistry that can happen in star-forming regions. So we also do have these outflows that could be one of those non-thermal mechanisms, putting grains off of the grain mantles back into the gas phase, and that is just through shuttering, or sputtering, or shocking those molecules off of the grain mantle. So there's lots of processes going on. We really have to do a lot of work to disentangle what's going on. So in interstellar space, we found over 300 molecules in interstellar space, ranging from diatomic molecules, such as carbon monoxide, all the way up to things with 13 atoms or more, or even hydrocarbons that polycyclic aromatic hydrocarbons that have up to 60 or 70 atoms. What I'm going to be looking at today is ones with about 6 atoms or more. We do have quite a few molecules, so this is, you don't actually have to read the details, this is just a show of like how many molecules are out floating around in space. So we're going to look at 6 atoms or more. There's still quite a abundance of these molecules that can tell us a lot about in some regions. So 2 main categories that we like to look at are on the left, complex organic molecules, and on the right, carbon chain molecules. So complex organic molecules are saturated molecules with 6 atoms or more. By saturated, I mean that all the bonds between the atoms within that molecule are single bonds, and it has the maximum number of hydrogen atoms that it can inside that molecule. An example of this is methanol, CH3OH, and typically these molecules are formed in regions in interstellar space that are rich in carbon monoxide. This is typically found in high mass hot cores, so star-forming regions that are forming stars greater than 8 times the mass of our sun, and also in low mass hot corinos. So we call hot cores of low mass regions hot corinos, just a little smaller. Then on the other side, our carbon chain molecules have unsaturated carbon chains. So links of carbon atoms within your molecule that might have double or triple bonds. You don't have the maximum number of bonds in that molecule that you could. This is typically formed in regions that are rich in atomic carbon, and this is typically found in those dark molecular clouds, those pre-stellar cloud phases, and in very low mass protostars. An example of a carbon chain is propyne, just shown here, CH3CCH. So these 2 types of molecules have led to the categorization of star-forming regions into 2 extreme types of sources. On the left, we have hot cores or hot corinos that have abundant complex organic molecules in a very dense and compact and hot. By hot, again, I mean over 100 Kelvin region around the protostar, whereas the warm carbon chain chemistry sources could have an abundance of carbon chain molecules in the more extended warm envelope around the protostar, typically warm around 30 Kelvin. So this dichotomy in protostellar sources doesn't really capture the entire suite of molecules that we have. I'm completely ignoring nitrogen-bearing and sulfur-bearing molecules. But given what we know about protostellar sources, these are two very important types of sources that we can look into. So to elaborate on this a little bit, the reason why we could have these two extreme types of sources is their chemical evolution. If we have carbon, atomic carbon, in the very early stages of star formation taken up in carbon monoxide, that will deplete onto the grain surfaces in that cold prestellar stage. On the grain surfaces, you will have hydrogenation of that carbon monoxide, forming larger molecules such as formaldehyde, H2CO, I think at this point you're working again, H2CO, or methanol, CH3OH. As the protostar warms up, or as non-thermal mechanisms sputter off those molecules back into the gas phase, you will then have hot gas phase chemistry forming even larger complex molecules from formaldehyde or methanol as a basis. Whereas on the other hand, if you have carbon remaining in its atomic form before depleting onto the grain mantles, you'll have hydrogenation of atomic carbon forming something like methane, CH4. And then as the protostellar evolution continues, you'll have methane put back into the gas phase to have warm gas phase chemical reactions, forming your larger carbon chain molecules. That's when you could potentially get a warm carbon chain chemistry source. And so this is how your dichotomy could happen. You could either have a hot core source or a warm carbon chain chemistry source. There are two main reasons why you think there could be a difference between carbon being taken up in carbon monoxide versus staying in its atomic form. And that is one, either the duration of that early protostellar stage. If it's quick, carbon won't have the time to be taken up into carbon monoxide. The other explanation could be that it's an environmental factor. If there's UV irradiation from a nearby source, it could keep carbon in its atomic form rather than it being taken up in carbon monoxide.
Can I ask a quick question?
Yeah, for sure.
So the difference, so it's an initial condition.
Yes.
Thing. So is it the temperature? If it's not non-thermal, which you just described, what would set the difference between these two conditions? So is it that the one at the bottom is initial higher temperature?
Yeah, so we don't know for sure, like exactly. The two main leading explanations are the time scale. So if there's not enough time for carbon to be taken up, majority in carbon monoxide, you'll have the bottom scenario. Or if it's environmental, if you have UV irradiation from a nearby source, it'll keep carbon in its atomic form. And that could lead to the bottom scenario as well. So those are the two leading explanations.
And I think in the previous slide you mentioned 100K versus 30K. 100 Kelvin versus 30 Kelvin.
Yeah.
That's in the last phase, right? That's
yeah, that'll be around here when the protostar is warming up the region around it. So you could have the hotter over 100 Kelvin, really close to that source later on in the protostellar formation, but the more extended envelope might remain at something 20 or 30 Kelvin.
So how fast will be the first phase to occur only the second part of it?
I think on the order of 10 to the 5 years.
So it has to be lower than that for the first phase to be okay.
So in these protostellar studies, there's still a lot of open questions focusing on carbon chain chemistry specifically. We want to know, is it prominent or some or all of the high-mass star-forming regions in our galaxy? What are the physical conditions that carbon chain molecules exist in? Is warm carbon chain chemistry the main mechanism in which they're formed? And how do they compare to complex organic molecules? Do we have this actual strict dichotomy between two types of sources in protostellar regions? So during my PhD, We mapped 3 high mass star forming regions towards Cygnus X, a very large high mass star forming complex. We did this with the 100-meter Green Knight telescope and the IRAM 30-meter telescope in a wideband spectral survey. So during this talk, I'm only going to talk about 2 of these sources. One of them is called DR21OH. It's that very bright source in the top left of Cygnus X. It is a relatively young source. There's no indication that there's H2 regions yet in this protostellar evolution. This source also has several dense clumps within that more extended filament, so it's quite a clustered source. There's lots going on. That's one of the reasons why high mass star forming regions are harder to study than low mass, is typically they are quite clustered. So it's hard to disentangle what is necessarily going on in any one individual source. For comparison, we'll look at IRAS 2126. This is a relatively isolated and dense clump on the other side of Cygnus X. In comparison to DR21OH, it's a little bit older, but it's much more simple to look at. So just give you an example of what our spectra look at like. This is some of our spectra from DR21OH in the center of the main source. So we see that in GPT and in IRAM, we do see a suite of molecules. There's simple molecules from things like CS to OCS, some isotopologues. We also have several lines of one carbon chain species and a complex organic molecule. So just zoom in on this stuff a little bit so you can see it a little bit better. This is again DR21OH, but zooming in, instead of looking at that wide band, looking at small parts of that entire spectrum. So here on the right 2 columns, we have just a few transitions of methanol, not the entire number of transitions of methanol that we have, just a few. Some from formaldehyde. Formaldehyde is a very important complex organic precursor, so I'm going to lump it into the complex organics for the purpose of this talk. And we also have here a few propyne lines. So again, CH3, CCH, that would be our example of a carbon chain molecule. So this is just to show that these lines are actually real. They're not just kind of lines that I put in the broadband look before. But how do we actually get any information about the physical environment of these sources from those spectra? So this is an example of what our map looks like. In our data, we have both spectral information as well as spatial information. So this is just one integrated intensity map of a line of propane, CH3, CCH, and we do see that there's already structure that we can see many more dense clumps across DR21OH than just one protostellar source. But we're going to look at just one individual pixel. If I take this central pixel here on the main source of DR21OH and look at all the propyne transitions, it will look something like that. So we want to be able to model these lines through what we call a local thermodynamic equilibrium model. So that is built on the physical parameters source size, excitation temperature, which in LTE we can correspond to the kinetic temperature of the gas. We look at the column density, which is just looking at the number of molecules along the local site. We look at the line width of the spectra as well as the source velocity. And so with all of these physical parameters, we can build a model to try to fit the spectra. And so during my PhD, led by one of my collaborators in Nautilus and Jim Bostonelli, we developed the CASSIS LTE Python code. It contains a flexible LTE model that's based on the formalism of the CASSIS software, but is transferred into Python to have it be a little more flexible, a little more user-friendly. And so what we did during my PhD is develop this for the data cubes that we got from the GPT and the IRAM. So we can suit it to a data cube that we can loop this LTE model over all of the pixels in our map in order to actually get a map of the physical environment, a map of the density, of the temperature, of the velocity, of the line width that we expect to see across there. So next, I just want to show you some of those results. We'll start with IRAS 2126, our simpler source. Remember, it's just one protostar isolated. And so on the top row, we have column density. The second row, yes.
What is the input of the simulation? Is the properties of the protostar known? Who picks up the
Yes, so we have the main parameters that go into it. Some of these are known or can be known about the source, like the source velocity or the source size. That might be known, that might not be known. But we also have things like the temperature, the density, and the line width that can change depending on the molecule or depending on the exact environment, the spatial scale that you're looking at. So for a simple source like IRAS, we ended up just fixing the source size because we knew roughly what to expect within our beam as well. And we had an idea of the source velocity, but we left all the other parameters free since we just had one physical component that we were looking at. You'll see in DIR 21H that we'll have multiple physical components going into that model. And so you might need to have a little bit more of a refined idea going in so you don't have as many free parameters. So some of these things might be known, might not be known beforehand.
And how will this assume the LTE approximation? Is it okay to assume the LTE approximation? The local thermodynamic estimation?
Yeah. For these sources, I'll show you a couple of places where it's not. Actually, I've left that out of this talk. There are places where the LTE assumption did not hold in our source. So methanol, for example, can be a maser. That is one of the indications of high mass star formation. And so when we tried to do the LTE model there's one methanol line mainly that was problematic. We just ended up discarding that line from the LTE model. But we looked at given the temperature and the density of these sources, the LTE assumption there. So onto this graph. So in density on the top row, we have excitation temperature, velocity in the third row, and line width in the bottom row. Out of this graph, there are two main parts that I'd like to point out of our results. The carbon chains are the left two columns, and the complex organics are the right two columns. So first, you can see that the presence in these maps is starkly different between the carbon chains and the complex organics. The carbon chains have a much broader, more extended distribution, and they're typically you only get them up to a temperature of about 30 Kelvin, whereas the complex organics, you have them much more concentrated in a compact area around the protostar. And the temperatures in that area get up to around 60 or 80 Kelvin. So in our single dish observations, we don't have necessarily the spatial resolution to get down to that area right near the protostar that might be over 100 Kelvin, and we might be diluting the temperature results a little bit, so they might be a little bit cooler than what you might get with an interferometer. We're still seeing a stark temperature difference between the complex organics and the carbon chain molecules. The other point is that you can see the velocity structure is also quite different. We have a north-south gradient in the carbon chain molecules, whereas there is a offset when we get to the complex organics. I'll pull this out and just give you a little schematic of what this environment looks like. We have our photosolar source surrounded by a warm envelope. We have a large-scale outflow oriented south-north that has been also traced by carbon monoxide. And then we have this small-scale outflow that is oriented southeast to northwest that has been also traced by small molecules that we see in both formaldehyde and methanol.
The size scale of these images is tens or hundreds of the
Hundreds. Do I have a scale bar?
It's about 1.5 minutes, beside of a minute.
Our beam size is 10 arc seconds. We mapped it over 1.5 by 1.5 arc minutes. This is slightly smaller because we masked out a lot of the edge, and these sources are at about 1.5 kiloparsecs away.
It's like 40 arc seconds.
No, 1.2. No. How about the size?
The size of the.
Not
Yeah,
100.
like four.
It's thousands of it. I see.
So then, looking at the same results for DR21OH, again, DR21OH is a much more clustered source than IRAS-2126, so I'm going to focus on this region in the center, N44, which has our two main protocellular clumps across this filament. We'll call them MM1 and MM2, and those will be labeled in further diagrams. And these clumps, MM1 and MM2, are further subfragmented into 9 cores. So already a clustered source in N44 itself. And so this is the column density maps of the physical components that we were able to pull from our model. So in DR21OH, since there are multiple temperature and velocity components, we end up fixing a lot of the parameters in our model after both a look at what we expected from the literature and several tests. We were able to fix those parameters. In methanol, we ended up having 5 physical components, in formaldehyde 3, and in propyne 2. So those physical components we were able to match to the first 2 seen in methanol in this top row here, and formaldehyde in the second row. Spatial clumps of MM1 and MM2. In the third component, seen again in methanol, top row, and in formaldehyde in the second row, we have a molecular outflow just offset from MM2, or one-sided molecular outflow. Just off of MM2, and then seen again in methanol and also in propyne, CH3CCH, we have a more extended envelope around MM1 and MM2. And if I can get the just over, yeah, just over in the top right here. So we are, even from our single dish beam scale, we can start to really disentangle a lot of the actual physical structure in such a cluster source. And so if we look at DR21OH in total, on our broader map, we have these 6 dense clumps along the filament. These had temperatures of about 20 K, or the extended ridge had temperatures of about 20 Kelvin. With these dusty condensations potentially having high mass structuring going on in them. And then you have further subfragmentation of the scales that we get from MM1 and MM2. And you think this is all well and good. We have these kind of like spatial temperature and velocity correlations to what we could know about the source, but that doesn't actually tell us anything about how these molecules could arise in these sources. It doesn't tell us about the formation or destruction rates. So then we turn to Nautilus, which is a chemical evolution code that will allow us to probe those formation rates. The Nautilus code assumes that there are 3 phases in interstellar space. There's the gas phase, there's the surface of the grains, and then there's the grain mantle. In all of these places, you could have chemical reactions going on, and you could have different formation rates producing these abundances. So this first graph is for IRAS-2126. We're looking at propyne in red and methanol in blue. The dotted line that goes across the graph constantly is the abundance that we found from our observations. And then the solid line is the model abundance over time over the protocellular evolution. So the 2 points that we found for IRAS-2126 is that in this top graph, we see that propyne appears in the gas phase the model abundance matches the observed abundance. Again, I do not know what pointer is. So it matches here, and we see that it's through thermal mechanisms. Propine appears in the gas phase as the protostar warms up the cloud to temperatures of about 20 to 30 Kelvin. So this matches what you would expect from warm carbon chain chemistry. You notice though that the blue solid line in the top graph for methanol in a model does not match our observed abundances at any time. So we needed another mechanism in order to produce the methanol abundances. So we ended up simulating a shock just by spiking the density and the temperature in the model. And we found that in this one, we see that the model abundances match the observed abundances during this protostellar evolution. But so we found that methanol requires a shock to sputter these molecules off the grain surface and into the gas phase. So that's for IRAS 2126. And then if we look at DR21OH, we do the same kind of model. So again, the graphs that I'm showing you have here I'm looking at formaldehyde in the top graph and propine in the bottom graph. The constant line across the graph is the observed abundance that we see. And here, since we had multiple physical components, each of those lines corresponds to one of the physical components. And then the colored line that varies over time across the protostellar evolution is what we found from the model. So in DR21OH for formaldehyde, H2CO, we see that it appears in the gas phase as the protostar warms up the cloud. For propine in the bottom, it also appears in the warm-up stage through this thermal mechanism, but only if the extinction is low. And when we actually looked at the formation rates of propine, we found that it was forming on the grain surfaces and not in gas phase, as you would expect with warm carbon chain chemistry. And the reason why I'm not showing methanol in DR21OH was for this one, we were unable to reproduce the abundances that we found from our models with the densities and temperatures found with any of the 10 ways in Nautilus that we could think of. Methanol is a known problem child in astrochemistry, so that's not unexpected. We just have to do a little more digging in order to figure out how methanol can be formed in this source. So overall, from this look at warm carbon chain chemistry and complex organic molecules in these protostellar sources, we're kind of left still with a question mark. There's not a clean dichotomy between hot cores and warm carbon chain chemistry sources. There have been some other studies recently that have been looking at the possibility of hybrid sources, where it could just be a difference in the spatial regimes that you're looking at. You could have the same source having hot core properties on small compact scales and warm carbon chain chemistry properties on the more extended envelope scale. So not enough sources have been studied in protostellar sources to actually give us a clear look at what's going on here. But there are lots of next steps that you could immediately do off my PhD work. We do want to look at what other molecular groups are telling us. That look kind of ignores sulfur-bearing and nitrogen-bearing species, which are also quite abundant in protostellar sources. We do have estimated data in hand, and IRyA has all the data in hand for these sources that we can actually look at those hot core scales. We do want to look at if the chemical makeup seen in these three sources is actually matches to those on a more broad sample. Observing more sources would allow for statistics to be done. It's just very hard to get to the actual kind of sensitivity that you need on radio telescopes at the moment in a reasonable observing time. So it's one of the reasons why we chose three sources was the number of hours that we could ask from the GPT and from the IRAM 30 meter. And in what ways can we develop this LTE model a little bit more refined to have it better suit large data sets with wideband and mapping information? And so that leads into what I'm doing here at IRyA. So existing telescopes like the GPT and the IRAM 30 meter have propelled the astrochemistry forward, but One major part about these single-dish telescopes is they don't have that spatial resolution needed to actually probe the emitting regions where these molecules could come from. So they suffer what we call beam dilution for compact sources. If a molecule has very weak emission, it will be spread out in your beam and you might not be able to detect it. And we can't reach detection limits needed for detailed hot core studies in reasonable observing times. But these single-dish telescopes have been very important for astrochemistry. If we look at this graph of number of detected molecules over years divided by telescopes, we have the NRAO 36 foot in brown, the IRAM 30 meter in orange, the big speck here, the GBT 100 meter in blue. So these are the telescopes that are leading the way in actually detecting molecules, but that's about their limit. You can't probe the small emission scales, you can't do wide surveys on them, but they're really important for actually letting us know what is out there. So if you move over to something like ALMA will be able to probe those small spatial scales that you really want to get to. However, ALMA in millimeter wavelengths, your spectra can be so densely packed with lines that you get what is called line confusion. You can't actually have any line-free channels in your sources, so it's really hard to actually figure out what molecules are in that spectra. It takes a lot of work, as I'm sure Esme can tell you, to actually figure out what's going on in these. So this is an example of ALMA spectra from a hot core on the top row and from a hot Crino in the bottom row. There's a second problem with ALMA data. At millimeter wavelengths, your emission could potentially be obscured by dust. Desmoneo in 2020 showed that an ALMA comparison to the very large array at centimeter wavelengths showed that the ALMA emission or the millimeter emission was quite obscured, and so you couldn't actually probe the hot Crino area. So ALMA has been great for hot Crino studies, but does have its limitations. So that's where the next generation very large array comes in. It will provide the next generation of these studies, as its name suggests, with very broadband observations. Depending on which band you're looking at, you could get up to 20 gigahertz of instantaneous bandwidth. It will have high spectral and spatial resolution, high sensitivity, so it will be able to probe those small scales of the hot core, the disk, the outflow, really where we can find how molecules are evolving over the protostellar evolution and how they could potentially be inherited into planetary disks. And also in the centimeter wavelength regime, it will both look at some key molecules that we already know of, like ammonia or methanol, but it will also reveal yet undetected heavy complex molecules. In your rotational transitions, the heavier your molecule is, the more shifted to lower frequencies it will be. So the centimeter wavelength regime is very key for some of those prebiotic molecules or potential prebiotic molecules. So what I'm doing here is looking at simulated observations for these complex organic studies. This is similar to work that's already been done here at IRyA. I think quite a few of you were involved in a paper that came out last year looking at observations of ionized gas. There's another paper that came out a few years ago from Europe that was looking at simple molecules in high mass structure regions. But we're now looking at complex organics. So we're using the Astrophysical Environment Code, which was published last year by Pierre Michel et al., who actually works across the hall from Sandrine and Emmanuel over in Toulouse. So very close collaborator with us. In 8th, we're able to get a physical model of our protostellar source of the compact object, the disk, the envelope, and the outflow. And then this physical model can interface with the radiated transfer code, RADMC3D, the chemical evolution code Nautilus that I mentioned before, and with something called Imager that will produce our synthetic images. So this map here on the right is a density map with temperature contours, setting up our physical model for a solar mass protostar. So if we move on, if we let this evolve, if we put this model into Nautilus and we start to focus on some of those complex organic molecules that we are interested in, we have these abundance maps pop out. All of the color bars on these graphs are the same for easy comparison between the different molecules. So we can start to see the outflow is completely masked. We're ignoring the chemistry in the outflow. We have the disk that marker. The disk going here up to about 90 AU away from the central object, and then the more extended envelope. And we do have some chemistry influence just on the outside of the outflow here. So we already start to see some stark differences between these molecules, even for molecules that you would expect, say, dimethyl ether here in the bottom row, second from the right, and methylformate, bottom row, second from the left. There have been some studies to show that these could potentially have a either mother-daughter or sister relationship in their chemical evolution. But here we're starting to see that based on the chemical reactions that we know of within Nautilus, that dimethyl ether, pulling out this marker here, has a much stronger abundance outside of the outflow than something like methylformate. We also have, if you look at the disk, you start to see some differentiation, say, in propine between the inner disk and the mid disk. And then our abundances really fall off towards the outer disk. So this model, the physical model, is built on what we call a grid of particles. So each of these points within this model corresponds to one particle that evolves over time and ends up being the input for our chemical evolution. So we can look at one individual point and look at how those same 8 species evolve over time. So if I look at a particle, right, in this blue X here, it's in the inner disk, it will have this temperature and density evolution over the protostellar evolution. The protostar turns on in about 150,000 years, and we let it run for another 150,000 years, just into the end of about the class 1 stage where the envelope is dissipating. And so this temperature and density evolution leads to these molecular abundances. So I do want to just compare this to what we would instead see from the middle disk. A particle here in the middle disk just moving a few more about 10 AU, I believe, further out in the disk. We have a very similar temperature and density evolution, but we do have stark differences in the abundances that we're getting off of here. So say for acetaldehyde, CH3CHO, and methylformate, HCOCH3, the gray and the brown lines here, quite a low abundance in the middle disk, whereas in the inner disk, we have a sharp spike in the brown and in the gray lines. And this is just showing that it's really, really important to be actually able to have those, that small spatial scale on the spectrum to be able to differentiate what's going on in the different regions of the envelope and the disk. In contrast, if you move just out of the disk to a region that's in the envelope but near the outflow, you'll have a much different chemistry. So this is just initial results looking at what could potentially be going on in this source. And what we want to do then is you need to take your abundance maps, you look at specific transitions, you build your emission maps based off of those transitions and your observing parameters from the telescope, and you can create synthetic images. We're right now working on getting the NGVLA configuration working in Imager. And for those of you who know or who do similar work, you may be wondering, why aren't you just using CASSA for doing simulated images? One thing is that Imager is the software that it interfaces with, and it would be really cool to actually develop the ability for Imager to have user-specified configurations. So say putting in my own configurations for the NGVLA. That capability is in CASSA. So if we can't get it to work in imager soon, we will be moving to CASSIS. So this is where we're at the moment. We're trying to develop these synthetic NGVLA images of complex organic molecules. This colloquium talk was mainly based more on fitting me into the schedule and filling the schedule rather than actually finishing a project. So please stay tuned for these results. There are also things that we do want to do with these results. We really do want to look at where we expect to see these complex organic molecules arise and what diversity we can expect to observe with NGVLA. We want to look at what types of sources, so either by mass, by distance, and telescope configuration should we prioritize when the NGVLA comes online. And we also just want to take a quick look at how the NGVLA observations, how we'll expect those will compare to current ALMA observations. And so with that, I will leave you with my summary, and I'll be happy to take any questions.
Okay, we have plenty of time for questions.
So in the diagram that you put the two different options, whether you stay with carbon in the envelope or not.
Yeah.
What are the densities, the physical routine that you are talking about in that case? Because my impression is that all the analysis that you made later correspond to much more dense regions. And this is more like the diffuse medium into the molecular cloud. You know? So there is a wide range of densities between the left and the right.
Yes. Yeah. So I believe in the early stages, you could have about 10 to the 5, like an density of 10 to the 5. Whereas moving into the actual like protocellular environment in those hot core densities, you could have like 10 to the 7, 10 to the 8.
But 10 to the 5 here, so you can see the carbon there alone at 10 to the 5 density. It's quite high now. It's kind of in the middle of the molecular cloud. So I wouldn't expect much carbon isolation.
Okay. Yeah. From my understanding, those are the densities that we would have in like the pre-stellar
yes,
region.
in the pre-stellar, yes. In the pre-stellar region,
Yeah.
yes. But I'm wondering whether at those densities you will have carbon not going already into the CO, because it's inside of the molecular cloud. So most of the carbon has already gone into the CO. So, and also you mentioned UV radiation, but if you are inside the molecular cloud, there shouldn't be much UV radiation.
Yeah, that is, so again, these are still two just like the leading ideas. There was one study, there could be UV radiation on the edges of the envelope. So in our study of geothermal, we could only produce the propine emission when the extinction was low, so say on the cloud edge. There was also a study done, I believe it was published in 2016 by Charlotte Gastel, and they were actually looking at a source that ended up being very asymmetric in its methanol and I believe it was cyclopropionality emission. And so you had the methanol in the very in the more shielded part of the source, and cyclopropionality in your carbon chain chemistry was happening in the part of the source that was exposed to UV radiation. And so it might be like something that just happens on cloud edges or in like lower density regions.
Hi, Pam, thank you for this presentation. I wonder how difficult it is to identify lines in molecular, because when you show the spectra, I saw many, like a lot of.
Yeah. So you're wondering how you actually go from the spectra to being able to label these?
Yeah.
Yeah, it's a good question. People are trying to automate this process, but it's very, very hard. So typically it is just done by hand. I use the software called CASSIS. You are able to have a catalog of molecules, and you can build a you can just start off by either doing just like Gaussian fits to the spectra or doing a kind of faux LTE model of these sources. So you take prior information of what molecules you say you would expect to see. So methanol is quite an abundant molecule. I'm going to put it into my model and see formaldehyde also is quite common, carbon monoxide, carbon monosulfide. So the molecules that you say you would expect to see, you put it into the model with your frequency parameters, so the bandwidth that you're looking at and the velocity of what you expect the lines to be at, because that could produce a shift in your spectrum. And you try to fit the data. And so you can start off with just doing like one molecule at a time, going through being like, I know there should be a very strong line of methanol at about 96 gigahertz. I'm going to try methanol for those lines. And then as you keep on building up the model, you start crossing off some of those lines, but you start to move into maybe more rare molecules that you wouldn't necessarily expect to see, but could be around that frequency range. So CASSIS has a very large catalog of molecules that you can try to fit it. But you'll then see that some of these lines are labeled with U, and that is something that where I fit a Gaussian to it, it has a good signal to noise ratio. I think it's a real line, but there's no molecule in our catalog that actually makes sense. There's either just no molecule completely that corresponds to it, or there could be a molecule, but it doesn't actually make physical sense for that specific molecule to be the source, and that's certainly for the very large molecules. So it is a little bit of, you have to have prior knowledge of what you would expect to see, and a lot of trial and error of just trying to fit these, just trying to fit the data. So that's why for something like this, it does take a lot of time. Those ALMA data I showed you where the spectra were just like covering every single channel, like it's quite hard to actually end up identifying all of those lines. Just a lot of time and trial and error.
Thank you.
Why can't you automate this? I mean, you have templates that you can just compare with observation.
I think the difficulty just comes in actually then you still have to go through it and confirm that that's actually what you're seeing.
You mean there are many degeneracies built in when you start comparing lines?
Yeah, there could be
It's supposed to appear at a given frequency, yes?
Yes, but you could have lines that are blended together, or you could have things that aren't lines. So I think, say for example, these lines here, at about 290 gigahertz, there's a whole bunch of methanol lines, but there's also something like dimethyl ether in there. You would expect to see methanol much stronger than dimethyl ether, but if they're at close enough frequencies that you can't actually distinguish them in one like Gaussian fit to it, then you're not going to necessarily know. People are working on automating this. I just don't think maybe it's as people are as confident in the automated results as if people are just doing it by hand. Maybe in the next couple of years we'll actually see that working.
More questions? Anything on Zoom? Nothing? Okay, well, let's thank Pamela for a very nice talk.